All right, let's just jump right into this explainer. Look around your house for a second. Think about your laptop, and then think about your microwave. Your laptop is an absolute powerhouse, right? It's running thousands of background apps, pulling down data from global networks, processing crazy graphics all at the exact same time. But your microwave? It literally does one thing. It heats up your food. Now, both of these machines have processors. Both execute software code. Fundamentally, they're both computers, but their underlying architecture, completely different worlds. Today, we're going to unpack one of the absolute most crucial concepts in computer engineering and take a look at the invisible computers that quietly run our entire modern world.
So that brings up a really fun mystery. Why is it that your smartphone can do, countless tasks, but your washing machine just follows one? Well, think of your smartphone as the ultimate Swiss Army knife. It's got a tool for absolutely everything. 1 second you're firing off an email, the next you're playing a massive 3D game, and a minute later you're using GPS to find a coffee shop. But the washing machine? It's more like a highly precise scalpel. It is engineered with extreme precision for a singular purpose. Its processor is never ever going to try to boot up Google Chrome. It only needs to understand water temperature, drum speed, and a timer. What makes these two computers fundamentally different isn't just the software. The difference is deeply rooted in how their physical hardware is actually put together. Which brings us to Section 1, General Purpose versus Embedded Systems.
To really wrap our heads around this, we've got to draw a clear line in the sand between the two major categories of computers. On the general purpose side, you've got your desktops, your laptops, tablets, and those massive server farms. These are built for ultimate flexibility. I mean, as long as someone writes the software for it, a general purpose computer can probably run it. But then, on the embedded side, we have extreme specialization for a single task. We're talking about the brains inside traffic lights, life-saving medical devices, the ATM down the street, or huge factory robots. They don't need to juggle hundreds of random apps. Instead, they are hyper-optimized for speed, incredible efficiency, super low power consumption, and, above all else, just absolute rock-solid reliability.
All right, let's move into Section 2, comparing their architectures. Because here's the thing, a computer's purpose completely dictates how its hardware is built. You literally cannot design a versatile gaming rig the same way you design a heart monitor. The engineering constraints are totally different. For a general-purpose machine, you're relying on a beefy CPU, massive amounts of RAM, and huge solid-state drives just to store your varied files and heavy operating systems like Windows or Mac OS. Because of all that, they suck up a ton of power and cost a lot of money to make. But look at embedded systems. Instead of a standalone CPU, they use what's called a microcontroller, or MCU. They've got tiny amounts of RAM and just enough flash memory to hold their single dedicated program. They run on incredibly lightweight real-time operating systems, or honestly, sometimes no OS at all, just raw bare metal code. The result? They cost literal pennies to make, draw almost zero power, and are built to respond to real-time events instantly.
And all those differences in specs, they lead directly to a massive difference in physical layout. A general-purpose architecture is sprawling. Think about a PC motherboard. It's like a giant puzzle. You've got the CPU slotted over here, sticks of RAM snapped in over there, a massive graphics card plugged in somewhere else, and a bulky power supply feeding the whole shebang. All these separated components have to talk to each other by sending data across the board through pathways called buses. It takes up a lot of physical space. Embedded architecture, on the other hand, takes all of those separate components and shrinks them way, way down, integrating everything onto one single tiny chip.
And that tiny chip has a specific name. It's a microcontroller. By definition, a microcontroller is a single integrated circuit that contains a processor core, memory, and programmable input/output peripherals. It acts as the beating heart of an embedded system. Guys, this is the magical piece of engineering that actually makes the modern world possible. By squeezing an entire computer system onto one tiny piece of silicon, engineers can embed intelligence into practically any object on the planet.
Just look at everything packed inside that single microcontroller chip. It's wild. You've got the CPU doing the math, you have RAM for temporary data, and flash memory storing the permanent code, but you also have built-in timers. You've got GPIO pins, that's general-purpose input-output, to turn things like motors and LEDs on and off. You have an analog-to-digital converter, or ADC, which lets the chip read real-world analog signals, like a temperature sensor, and translate them into digital ones and zeros. It even has dedicated communication interfaces built right in. It is an entire, self-contained universe on a chip, no bigger than your fingernail. How cool is that?
So let's jump to Section 3. The world is embedded.
If these microcontrollers are really so small and cheap to make, how many of them do you think are surrounding you right this very second? Seriously, look around your room. You've got your Wi-Fi router, your smart speaker, the AC unit, your TV. What about outside? Every modern car rolling off the assembly line today contains over 100 independent embedded computers, all talking to each other. Aircraft have thousands of them. Automated factories use literally millions of them. When we think of computers, we naturally picture laptops and desktops, but get this staggering statistic. Over 98% of all processors manufactured in the world today are used inside embedded systems. 98%! Only a tiny 2% are used in personal computers. We live in a world entirely run by invisible, hyper-specialized embedded computers. They are the silent workforce of humanity.
Okay, Section 4, the need for real-time performance. Now, you might be wondering, why not just use general-purpose processors for everything if they're so insanely powerful? Why go through the trouble of designing these specific embedded architectures? Well, it all comes down to one of the most critical concepts in engineering, the need for real-time performance. See, a general-purpose computer just isn't optimized for high-stakes instant control. If you click a button on your laptop and it freezes for 2 seconds because it's downloading an update in the background, it's annoying, but it's fine. In the embedded world, though, a 2-second delay can be catastrophic. Consider your car's airbag system. This is a system that simply cannot wait. It must react flawlessly. Step 1, the sensor detects a sudden collision. Step 2, the microcontroller instantly processes that force data. Step 3, the airbag deploys. And that entire sequence must happen in exactly 20 milliseconds. General-purpose computers with their heavy operating systems and background tasks simply cannot guarantee that kind of dedicated, split-second, real-time control. Embedded architecture is absolutely required to make it happen, without fail every single time.
Bringing us to Section 5, 2 tools for different jobs.
Ultimately, what we're looking at here are 2 tools for 2 distinctly different jobs. General-purpose systems are super flexible machines capable of running countless applications. They focus purely on versatility. Embedded systems are specialized computers designed for dedicated tasks, focusing on efficiency, reliability, and real-time execution. Neither one of these architectures is inherently better than the other. They just solve entirely different engineering problems. Understanding this distinction is really your very first step toward truly grasping how modern electronics are designed. Which brings us to the ultimate question as we wrap up this explainer. Now that we know embedded systems rely on microcontrollers and general-purpose computers rely on microprocessors, what is the absolute true technical difference between the two? And when an engineer sits down at a blank drafting board to design a new product, how do they know exactly which piece of silicon to choose? That choice dictates the success or failure of the entire project. Think about that as you look at the devices around you today, and we'll unpack the fascinating world of chip selection in our next deep dive. Thanks for learning with me today.